This talk will be presented by myself. My name is Ajay Gulati. I am a member of R&D staff at VMware. I have been working on storage management related projects for almost 3 years now. Storage IO control is one of the features that I worked on. And there is a tech preview on storage DRS also, which is one of the projects that I'm involved with. Along with me, the talk is co-presented by Chetan Kumar. He's one of the storage performance experts at VMware. And he has done a lot of storage projects, and a lot of publications have come out from those projects to really help some of the customer problems that they have faced. So one thing I would like to mention, I think this room looks like a fragmented disk right now. And if I could run sort of a defrag, and if people want to move either closer to facing the screen, closer to the mic, then that would be good. If you don't mind shouting from the back, I think that's fine. Okay, so let's go ahead with the... So if you have any questions, feel free to interrupt any time. We can have a very casual talk here, since we have very few people, and I don't think we have to worry too much about the time. We'll be doing pretty well. So let's start the talk. In this talk, we'll be talking about how to prioritize and isolate one VM from another, and how to get more out of your storage resources using a new feature that we launched in 4.1 called Storage IO Control. Here is a regular disclaimer about the talk. You must have seen it plenty of times by now. I won't spend any time on it. So what's the problem that we are talking about with this new feature? The problem that we are talking about is, in a regular data center environment, you have multiple VMs that are sharing the same underlying storage. And on a regular day, everything is fine and dandy. Everybody is pretty happy. And here, two of the VMs on the left-hand side are sort of high-priority VMs. They are running some workload which is more critical to the business compared to the right-hand side one, which is doing data mining. You won't worry about data mining result coming few seconds or few minutes later. So on a regular day, things may be fine, but at the end of some cycle, if somebody runs a heavy workload on the data mining virtual machine, the other VMs would really see the pain. And what you would see is this huge performance degradation that you were not expecting, and you would be taken by that surprise. Whereas what you would like to see in this case is that the VMs which are critical and which do expect a certain amount of storage latency and performance should not suffer just because of bad behavior of one other VM. And Steve actually mentioned this problem in his talk as well in keynote as a noisy neighbor problem. If you have a bad neighbor, you have to suffer some consequences, and we are trying to avoid that using this feature, at least in virtual environments. So when we talk about providing isolation, what sort of controls are we talking about? We have already been shipping some controls for CPU and memory for almost 4 to 5 years now. And for CPU and memory, we have been shipping something called shares. We also have reservations and limits. But for storage, we are going to be introducing a new feature now where you have the data store, and for each VM, you can also assign the shares. The semantics of the shares is very similar to what you are used to in the CPU and memory scenario. Along with shares, we are also introducing the limit. And reservation is something that I think I would like to get your feedback about, that do you really want storage reservations? And we can talk about some of the challenges in actually doing IOPS reservation in a storage environment. So what we are talking about here is that similar to the previous features for CPU and memory, you would have the same sort of semantics in terms of expressing your priority is shares and limits. So how does it all look in a typical data center environments that people run? In that case, you have multiple VMs running across different hosts, and the hosts are sharing the same data store using a clustered file system, typically VMFS. And in some cases, you might also be using NFS, but for the talk, we'll be mostly focusing on VMFS here. And the VMs on these hosts can interfere with each other, as we have shown in the previous example. And the goal of the feature is to provide the performance isolation while maximizing array utilization, because one can always think of a simpler scheme where you try to restrict VMs so much that even if some important VM is not using the storage resources, you would still not be able to give the resources to the unimportant VM. So we don't want to impact the overall array utilization, but when there is congestion, we want to be able to give priority to certain VMs. So in this, just to show how hard the problem is and why is it so difficult, why haven't we done this feature 3 years ago or 4 years ago, is if you notice in the diagram, we set shares to each of the VMs here. Just for the sake of example, I have put some shares numbers on each of the VMs. And there is no centralized controller. There is no single point of control through which all the IOs are going, and we can say that that point of control can run some algorithm that can do the proper scheduling. The only endpoint, the storage array, is perhaps the only point of control that you have. So in our scenario, we actually have distributed hosts where each host is running a set of VMs, and now they need to coordinate somehow so as to make sure that the VM running on a different host, sending a large amount of IOs, is not able to monopolize the workload that this host is accessing or the data store that this host is accessing. And it becomes a very hard problem when you have to do it in a distributed manner without any centralized control. And the top shares are basically saying that in this case, it's almost like different hosts should have different amount of importance on the SAN. So if you have different hosts running different number of VMs with some share values, they somehow should have different importance on the SAN itself. It's not, in order to give something to the VM, you have to first give something more or less between the hosts themselves. So before going into the technical details of the feature, let's just go over a quick overview of how the feature looks like, how is it to use, and what are some of the configurations that the feature actually takes. In order to use the feature, there are basically just 2 steps. Actually, there is only one step which you really have to do. Second step is sort of optional. And the step is that you have to enable the feature on the data store that you want to run it on. It's a per data store feature. You enable it on a data store, and then it would start running on just that data store. And there is no problem. The only reason I'm mentioning it because we don't have a button right now that says start on all. If you want to run it on all, that is actually very good, and you should just go and manually enable it on all of them. And the second, if you really want to have different priorities for different VM and all children are not really equal, then you can go and change the settings in terms of shares and limits for those VMs. So here is a screenshot where we are looking at all the data stores on the left-hand side in the data center, and we are at the configuration tab, and you can see here that there is, on the right-hand side, there is a small link that says storage IO control is disabled. Now, if you go on the corner and click on properties for that data store, you would get this view in which there is a small check mark which says enable storage IO control. And all you have to do is this heavy operation of checking it on, and the feature would start running. It actually took us 3 to 4 years to build this feature, including roughly 2.5 years of research and another 1.5 years of productization. But I think it will take you roughly 2 minutes to enable the feature on and start seeing the benefits of it. So once you have ticked that check mark on, you would see that the storage IO control is enabled. And if you go to the list of data stores, since in this particular case I have enabled it only on one of the data stores and not all of them, there is a column that shows you on which all data stores you are actually running the feature. And in this case, only one of them is enabled. The rest are all disabled. Once you're done with it, you may or may not want to do it, but for people who really want to go and change the IO shares, for each VM properties now, if you go to the disk, we have introduced a share and a limit value for each of the VM DK that you have. So in this particular case, the virtual machine has 3 hard disks, and we have set the shares to be low, normal, and high. You can pick your own value as well if you want to set it. And the limits here are set to 1500 IOPS each. One thing to note is that the limit is in the unit of IOPS. And if you understand your application better in terms of megabytes, then you would have to go through the effort of taking the megabytes, looking at the average IO size that your application does, and then you can put the limit in terms of that megabytes by IO size number. So the number here is in terms of IOPS and not in terms of bytes per second. Now, once you have done that, there is actually another nice screen that I think everybody should know about, is that for each data store, there is a tab called Virtual Machines, which actually shows you all the kids who are fighting for this ice cream. I mean, if there is one data store and there are 10 VMs running on it, only those 10 VMs and their share values are the one you are concerned about. If a VM is running on some other data store, that is not something that you need to worry about for this particular resource. So this view would show you the list of all VMs, the shares of all the VMs, and the limits of all the VMs. And this is a single view to actually compare that how much one VM is getting relative to its peers on the same data store. And you can look at it, and then you can decide to change the share values if you need to. Now, just to give a very simple example about what it would do if you actually went ahead and changed the share values and enabled the feature. In this case, we have two VMs. Both are running a simple micro benchmark, IO meter in this case, and they are doing 16 kilobyte random read IOs. And the shares are set in ratio 1:2. Now, if you look at in the red color, we are showing the IOPS and latency seen without the feature enabled. And in this case, you would see in spite of the fact we have set 1,000 and 2,000 shares, both VMs are seeing equal performance. And the latency is also roughly the same. If you look at the IOPS and latency in green with SIOC, you would notice that now VMs are getting different number of IOPS, roughly in ratio 1:2. And the latency is inverse of that. So what the feature allows you to do is it would reshuffle the performance or reshuffle the IOPS and latency from one VM to another. Unfortunately, we don't have the technology to give you more IOPS just by enabling the feature on the same storage that you have or less latency. But so far we can do is we can reshuffle the resources from one VM to another and protect one VM from bad behavior of other VMs. So if you notice the total number of IOPS with and without SIOC doesn't change. It would be cool to actually have the green number to be 5,000-6,000, then it would definitely put some vendors in trouble. So what you get is the VM IOPS are in ratio 1:2 once you have set the shares. Now let's look at some of the technical details in terms of what's really happening under the hood. What exactly is the system doing? Yes, please, you have a question.
If we have two data stores on the same RAID group, is there some way, does it realize there's no way I can tell it that they're on the same RAID group?
That's a very good point. I actually was going to cover that in best practices, and I'll talk about that issue there. If they're on the same RAID group, what to do. So let's look at some of the technical details. Here is an example where we are actually running some workload on 4 hosts, and there are 6 VMs. And you can notice that on the first 2 hosts, we are running VMs with file bench workload, OLTP workload in this case. And on the next 2 hosts, 3 and 4, we are running a IO meter workload. And on the top, I'm showing the VM share values that we have set. And on the bottom, I'm showing this just the sum of the share values on the host. That's not a number that you need to worry about, but just for the sake of explanation, I have summed them up, and I'm showing that number here. Now, if you run this system without storage IO control, what you would see is that host 1 and 2, in spite of the fact that they are running VMs with different amount of shares, are roughly seeing the same throughput. Similarly, host 3 and 4, they are running VMs with different importance, but they are seeing the same amount of throughput, which is not what you wanted. So instead of being in ratio 3:2, it's actually in the same ratio. And what you would notice is that VM shares are not really respected because VMs are running on different hosts. And if you happen to be running with 10 other VMs on one host, whereas one VM is running independently on the other host, he would actually be able to get a lot of benefit of running alone and not with 10 other VMs on this host. So host gets equal IOPS where they are actually dependent on the VM placement. This is the key takeaway from the slide, that if DRS somehow or for any other reason you move your VMs around because of the host level resources like CPU and memory, and it turns out that you put your critical VMs, 5 of them on the same host, which is a lot of CPU and memory, then in terms of IO, they can really suffer from performance because one host typically keeps a certain number of outstanding IOs at the array. Let's say that number is 32 for some data store. Then these 5 VMs would struggle with 32 slots, and some other VM running just on one host would be able to get the benefit of 32 outstanding IOs. And that is what would make a big difference in terms of the IOPS that the VM are seeing based on who they are running with.
Ajay, let me ask a question.
Sure.
You said storage IO control was not running.
True.
Right? But if you look at the throughput of the VMs on hosts 1 and 2, the throughput appears to be in proportional to their shares. Don't you guys think so? Why is that?
True, that's a very good observation. So the point that Chetan is referring to is that if you look at this host or this host, right now we are not even running the feature, but just for that particular host, the VM throughput is in ratio 1:2. That is because what happens is the host is also running a local scheduler. So the feature, as I'll explain later, is in 2 steps. Host is running a local scheduler to distribute what a host is getting to the VMs in ratio of their shares. But what is missing in this piece is that a host should be getting more if he is running more number of VMs, and a host should be getting less if it is running less number of VMs. So even if you don't enable the feature, you would still see this behavior, or you can say this is partial benefit, that VMs running on a single host would get some differentiation based on the share values. But what is clearly missing here is that if you put 10 VMs on one host, all 10 of them would share something, whereas if you run 2 VMs on another host, 2 of them would share that value of resource. So what happens when we actually run it with SIOC? In this case, if you notice that the host level allocations, so each of the bars here is showing the host level allocation, which is further divided into the VM level numbers. You can see that the host 1 and 2, now they are getting overall in ratio 3:2. And that value further gets subdivided by the host local scheduler between the VMs running on the host in ratio of their shares. So technically, the feature is actually working at 2 different levels. One guarantees that an important host should get more resources, and the second guarantees that the resources that a host is getting gets further subdivided in an equitable manner based on the shares. Yes? That's a very good observation. I'm glad you asked.
In fact, you just stole my question. I was going to ask him about the same thing.
That's good. So the question is that how come this 20 is smaller than this 20? Is that the question?
No, why is that 20 smaller than the 210 next to it?
Which?
Second and third, host 2 and 3.
Host, okay. I think the answer is the same for that question that I just phrased and the one that you mentioned. And the reason it is different is because you have set the share values, but that does not mean that your IOPS exactly would be in ratio of that number. The reason they are different right now is because they are running completely different workload. In one case, you are running a OLTP workload, other case, you are running a IO meter workload. And I'll explain actually that particular question in a little bit more detail, but the short answer is that if you are running very different workloads, then even if you have equal number of shares, the IOPS are not going to be exactly equal, because we are not going to force the number of IOPS to be in the ratio of the shares. And I'm going to show what we are exactly mean by the share setting of 2:1. What are we making in ratio 1:2? We have to do something in ratio 1:2, and then you would see some differentiation. But this is because of the different workload. If I was running exactly the same workload, you would have seen more or less the same numbers as we saw in the IO meter case earlier. So how exactly are we doing it? What I just showed you is what we are doing, but the question is, how are we doing it? There are basically 2 main steps to it. First is we need to detect congestion. For any resource management scheme, you only come into play when there is a need for you to be there. If there is no congestion for a resource or there is no contention, you don't need somebody to be coming in and arbitrating the access. So the way we detect congestion is by monitoring the latency at the data store. And this is something that we have learned after many years of implementing various techniques, that latency somehow seems to be a more common currency to deal with. Low latency is always good. High latency is almost always bad. And if your latency is approaching high, most people agree that that means the data store is getting congested. It's very hard to do that based on an IOPS number, because IOPS can be higher or smaller because of many workload parameters, whereas latency high is almost universally a bad thing to have. And For that, there is a parameter called latency threshold. If the latency goes above that threshold, we basically call the data store to be congested. If the latency is below the threshold, we allow everybody to send the workload that they want to send, which is basically the philosophy that if it's not broken, don't worry about it. Yes? Actually, that is the only configuration parameter that goes with the feature. When I showed you the screenshot, there was a button called Advanced. And if you click on that button, it basically tells you are going to be changing this threshold. Do you really want to change it? And I'll cover why you should change it if you want in the best practices later in the talk. But that's the only configuration parameter, and it's configurable. Once we detect the latency, once we detect the congestion on the data store based on the latency, the feature basically controls the IOs issued per host. And that is done based on the VMs that are running on the host and the shares of the VM. So if a host is running more number of VMs with higher shares, he would be throttled much less compared to a host which is running few VMs with smaller shares, he would be throttled much more. So this would happen dynamically based on the number of VMs that you're running and the shares that the VMs have. Furthermore, it's not a static allocation. The overall scheme is very dynamic. What I mean by that is, if one VM stops sending IOs and the latency suddenly goes down, it would allow everybody else to fill in the space. And I'll show that with an example later on. Let's first look at what we mean by setting this latency threshold and what is the high-level philosophy behind picking this parameter. If you look at a lot of performance studies in which they increase the load on the data store, so I'm showing on the right-hand side a chart between the overall load on x-axis and the data store throughput on y-axis. And a lot of studies have shown this, that as you increase the load on the data store, initially the throughput increases, but after a while it almost saturates. And you want to put more load on the data store to the point where the throughput is increasing, but beyond that, the throughput benefit is gone, but you would get hurt by the extra latency because you have put so much more load that the throughput is not changing anymore, but as you increase it, the latency would keep on increasing. So you want the congestion threshold value to be such that you are able to put enough load to get maximum throughput out of the device, but no more. Because if you make the latency go any higher, you are just adding latency on the device without getting any benefit in return. So the mark here shown basically says that for that particular load, if your latency is, let's say, 25 milliseconds, then you want to operate your data store at 25 milliseconds to really get the most out of the data store without putting any extra latency. So for the most part, we have picked the default setting, which would be there when you enable the feature. You don't have to worry about it. And we don't encourage people to go and change it all the time. But if you really want to change it, we have picked a slightly conservative value. We have picked a value which basically is operating the data store at almost the high utilization regime. But if you say, I don't care about getting the most IOPS out of the device because that means I have to go up to 25 millisecond or 30 millisecond, I'm fine running the data store at 15 millisecond, losing some top 10-15% of throughput, then you can actually lower the threshold if latency is your key parameter for your applications, and you don't worry about sucking that extra 10% IOPS out of the device by really loading it more. So coming back to the question that was asked earlier, that how come the IOPS were not equal in the previous diagram when we set the shares to be ratio to 20 and 20, or for that matter, the 10 and 10, the sum of that was different from 20. So there are two main units that we actually experimented with a lot, and people are very used to those limit units. One is bandwidth and second is IOPS. But if you try to divide or if you try to allocate bandwidth in ratio 1:2, then an application which is doing large size IOs would really suffer a lot, because he would do few large size IOs and he would hit the bandwidth that he should get, and we would say you are not eligible for more bandwidth because of the shares that you have, but the cost of doing a 64K IO is not 16 times doing a 4K IO. So doing bandwidth based allocation is really unfair to applications that are doing large IOs. Similarly, if you go with IOPS, it is highly unfair for applications that are doing sequential IOs, because they would do sequential IOs, they would come back really fast, they would hit the IOPS number that they should deserve, but now we would start penalizing them for getting too many IOPS and start giving them to random workloads, which anyway cannot suck up more IOPS from the storage. So instead, what we divide is the opportunity to send the IOs to the array. What I mean by that is, if you look at the overall number of concurrent IOs that you can send to the array to maintain a certain latency, let's say 20 millisecond, and that number is 50 concurrent IOs. Once you send 50 IOs to the device, you are operating at 25 millisecond. Now we would take 50 and just divide that up by based on your shares. We would say if you have 50 total in order to operate under a certain latency, then based on your shares, you might get 5, 10, 5, 7, 9 out of that 50. Now it's your luck that you issue your 5 requests. If they happen to be sequential, array would do it really fast and you would be able to reuse the 5 slots. If you happen to be doing random request, you issue a request, array is going to take longer to finish your request, and you would be able to recycle the slot much slower. So what would happen is that we allow you to maintain a high efficiency if your requests are actually much more efficient on the array. And we don't penalize you for doing faster IOs or smaller IOs. We just give you the equal opportunity to send the request. So if all of them had equal shares, and let's say there were 5 VMs, they would get 10, 10, 10, 10, 10, but the number of IOPS won't match, because one of them could be doing sequential IOs, one of them could be doing random IOs, one of them could be doing different size IOs, so the IOPS number won't match. And I think that is one of the expectations, that don't expect the feature to dole out IOs in some proportion. What it would do, it would prioritize, and you would see difference in terms of overall IOPS behavior and latency. And let me just show that with a diagram here. In this case, we have 2 ESX servers. One is running 2 VMs, other is running a single VM. If you don't use the feature, what would happen is that these 2 VMs are sharing one queue, and this VM is getting the full queue on the other host. And even if the VMs are equal shares, as in this case we have 1,000 shares each, the VMC would actually get twice the amount of throughput if they were running similar workload compared to VM A and B. So VMC is getting unfairly high number of IOPS just because he is sitting alone on a particular host. If you enable SIOC in this case, what you would see is that it would take the array queue, which is shown at the bottom here. This is the total array queue, and it would slice it 1/3, 1/3, 1/3 between VMs. And in order to do that, it might have to change the host level queues and then further subdivide that into the VMs, but it would make sure that you are getting 1/3, 1/3, 1/3 for different VMs, even if they are sitting on different hosts. They don't have to be on the same host. So the way scheme works is actually completely distributed. Every host is making an independent decision based on the VMs that it is running, their share values, and it is adjusting the queue depth by itself. And even though they are running a separate control equation in a distributed manner, the way the equation is designed is that they converge to a value in proportion to the overall shares.
Is each host independently just looking at latency and then using that as the back pressure?
Exactly. So basically, every host can monitor the latency, and
It doesn't need a vCenter or something else as an overriding controller or some inter-host communication. It just uses the latency as the final driver.
so there is definitely no involvement of vCenter other than just enabling the feature. In terms of observing latency, just to make the scheme more robust, because what can happen in some cases is that different hosts can see slightly different latencies. In that case, what we do is we try to communicate the latencies on different hosts using a shared file, so that everybody sees the same value of overall average latency on the data store. Yeah, and then everybody acts independently. That's the single piece of information that they need to get. After they get that information, it's an independent decision and independent execution. There is no sharing beyond that point. And vCenter is actually not coming in. And Chetan would show you in some of the results that how quickly the feature acts because of this. If you were doing something through vCenter, then the information needs to go there. Somebody needs to make a decision. It needs to come back. It would take minutes. And the feature would actually act much faster, and you'll see that in the case studies. So in this case, if you were to set different shares, in this case we set VM A and B with 1,500 and 500 shares, and VM C to be 500 shares, you would see that the overall array queue would actually get divided based in proportion to the shares that you have set. And this is what the feature is trying to do. It is not trying to allocate IOPS in that ratio. So the number of IOPS can be different. Another key thing that we have introduced in 4.1 is that we have elevated the status of the data source to be the first-class citizen in vSphere. People have complained a lot about in last 2-3 years that how come it's so hard to get storage stats. It's very hard to see storage problems. How do I know what is the overall data store latency? Because what I'm seeing is the per host data store latency, but not the overall average. So in vSphere 4.1, we have actually introduced 2 new completely data store centric metrics, which is the normalized latency of the data store and the aggregated IOPS of the data store. This is some of the information that earlier you would have to actually log into the array to get the information about what's happening on the LUN. But in this case, if your LUN is being controlled by the ESX host only, we would give you the aggregate metric in vSphere directly. And we have also introduced a chart for the queue depths, because what we are allocating or what we are setting is the queue depth at the host. So there is a chart there that will show you how the queue depth of the host are being adjusted in order to handle the congestion. And if the queue depth is sitting at the default value of, let's say, 32 in this case, then basically it means the data store is not congested. As soon as the latency starts to go higher, the queue depth would start changing and coming down, but the way it would come down would be in such a way that it would come down slower for the host with more number of VMs, it would come down faster for the host with smaller number of VMs, and it would converge to values which are in proportion of your host level shares, which would further get divided between the VMs.
Ajay, there was a question.
To go back to a question that a gentleman asked before, which is if I have multiple data stores, multiple LUNs defined on a single RAID set, then all these numbers, they're still going to have to be, I have to figure that out. I've got 2 or 3 data stores sitting on one RAID set. I'm going to have to add all those up to actually see what the performance is.
Of the RAID group, yeah. So this will give you the data store level number, and then if they're on the same RAID group, you would have to add them if you want to get the RAID group performance. Right. Okay, at this point, I would like to give the floor to Chetan to walk you through some of the real exciting case studies and really put the technology to use.
Thanks, Ajay. I don't want to stand there and be at risk. So is it okay if I stand here and talk? I don't know how Ajay managed to stand there.
It's enough space.
So far, you've been reminded of the painful problem you've been facing, especially with storage in virtual environments. And Ajay also introduced a solution that can help you mitigate this problem. What I will do is show some of the results of experiments that were done in VMware Performance Engineering Lab, which will highlight the capabilities of this feature. The workload that was used for all the experiments that I'll be discussing is called DVD Store. This is an open source online e-commerce workload. It's supposed to mimic an online store where users can log in, buy DVDs, search for DVDs, and things like that. It's a very simple workload, supports multiple database sizes. You can configure it the way you want to do a performance estimation that fits for your environment. The first case study will be talking about effect of setting disk shares. Ajay discussed this at length, how setting disk shares can affect performance of a VM, how setting disk shares mean that storage IO control goes and adjusts the queue slots for that are being given to each VM. Experiment, the test bed used for the experiment was something like this: 2 physical hosts, 4 VMs running on these physical hosts, and DVD Store was installed in all of the VMs. DVD store was running on a SQL Server database. The data and the index files that belong to DVD store of all the VMs were placed in virtual disks, which were in turn placed on a single VMFS data store. And for the second part of the experiment, storage I/O control was turned on this data store. The user load for DVD store workload is given in the table on the right-hand side. One of the VMs was identified as a critical VM, and the user load configured for this VM was the highest. First, the workload in the critical VM was run by itself. No other VMs were active. So the VM had the entire data store at its disposal. It was running happily. The performance obtained from it was normalized. This will serve as baseline for the comparing the performance of the same critical VM, but when other VMs are running. In the next phase, the DVD store workload in the other 3 VMs were made active. But because there was no control management scheme here, you can see that all of the VMs were contending for the queue slots, and the queue slots were randomly given to these VMs, which meant the performance of the critical VM dropped by almost 40%. And this is a typical case that happens in the virtual data centers. Next, storage I/O control was turned on. Shares were set on all the VMs. The other 3 VMs were given 200 disk shares, but the disk shares of the critical VM was varied. I'll show you the effect of setting disk shares on the critical VM and how it improves performance. In the first case, critical VM was given a 500 disk share, and storage I/O control immediately detected that there is a congestion condition in this setup, and it went and adjusted the queue slots that were given to all the VMs across both the hosts. As a result, the critical VM was given the highest queue slots of all the VMs, and because this critical VM now had more queue slots, it could issue more IOs, which meant the performance of the DVD store workload that was running in this VM improved. It improved to 80%. But this was still not sufficient. In the next step, the disk shares was increased further and the performance improved further. Now at about 1200 disk shares, the performance went up to about 90%. In the final case, the VM was given the highest number of disk shares, and that's about 4,000. And as you can see, the performance went up to about 95% of its best case. What this experiment shows that by setting the number of disk shares appropriately, you can expect to see better performance than not having any kind of control mechanism. But the problem is, yes, the critical VM was given higher number of queue slots, but what if that VM doesn't use all the queue slots? Then the queue slots would go waste, which means your storage device would remain unused during certain periods of time. When the VM is not using all the queue slots, the device would go wasted. You could have probably given the device to somebody else needing higher bandwidth. What should you do? Should you go and change the disk shares? But that would be not feasible, right? You cannot expect to keep changing the disk shares based on the load levels of your VM during any given day. How does storage I/O control handle this situation? This experiment discusses how storage I/O control manages this situation. The experimental setup for this contained 3 physical hosts, and this time the critical VM was running by itself on the 3rd physical host. DVD store was installed in all the VMs. The data and index files of DVD store was running on a shared data store. They were placed on virtual disks, and all these virtual disks were placed on the single shared data store. The user load is given on the right-hand side. Again, the critical VM had the highest number of user load. In the first phase, all 5 VMs were running, And this led to congestion, which was detected by storage I/O control. The latency, the congestion threshold for this experiment was set to 20 milliseconds, and the latency was higher than this one. So storage I/O control started throttling the queue slots that were given to the VMs based on their disk shares. And since VM5, the critical VM, had the highest number of shares, it experienced the highest throughput of all the VMs. The throughput of the other VMs were in proportion to their disk shares. In fact, you can see that in the vertical bar at the bottom, which shows the individual throughput of the DVD store workload that were running on all the VMs. They were, you can see that they are somewhat in proportion, or you can expect them to be in proportion to the disk shares, but I will show you how close they were. In the second phase, the critical VM, the DVD store workload running in the critical VM, stopped issuing I/O requests. It was not active. At this stage, if storage I/O control was not dynamic, you can expect what happens. A huge chunk of the queue slots would go wasted, right? Because nobody is using that. But storage I/O control detected that, hey, the critical VM is not using its queue slots, so I should give these queue slots to the other VMs that were active at the time. And it did that. Because it did that, the other VMs suddenly started seeing higher throughput compared to their phase 1 value. You can see that in the graph on the top, and the graph at the bottom shows that still the throughput percentage was somewhat in proportion to their disk shares, but I'll show you how close they were in a moment. In the third phase, the critical VM became active again. At this time, storage I/O control detected, this critical VM is now issuing its I/O requests, so I should give back all the queue slots that were given to it in phase 1. And it did exactly that, and as you can see, the throughput of the critical VM immediately went back to its phase 1 value in a matter of few seconds. And the throughput of the other VMs dropped back to their phase 1 level. There was a question.
VMs 1 and 2 both have disk shares of 500. 3 and 4 are 50% larger at 750. Yet, looking at just the color blocks, in the second diagram, that appears to be about proper, but the first and second is way off. Why?
It's a great question. Actually, there are a number of reasons. One, storage I/O control manages the queue slots within the range of the maximum queue depth that is set in the driver in a host. And because for the host that was running the critical VM, the maximum queue depth was 32, the storage I/O control couldn't increase the queue slots more than 32. And all the extra slots that should have been given to that host was now being distributed to the other host. And in this case, because host 2 had about 1,500 shares compared to host 1, which had only 1,000 shares, host 2 got undue advantage because of the limitation of storage I/O control not able to expand beyond the max queue depth driver. That is one reason. Second thing, the workload itself had this undeterministic patterns where the workloads running in the VMs on host 2 were issuing different number of writes compared to the VMs that were running on host 1. And as you know, if there are a lot of writes, the latency could drop because these writes are being served by the cache of the storage array compared to the reads. So that's another problem here. There is a white paper that has been published on VMware website which discusses all the results at length. And we can also discuss offline about this one after the talk. So as I told you, let's compare the shares with their throughput percentage. And as you can see, the throughput of each individual VM in each phase was proportional to the disk shares of the VMs in all the phases. And the gentleman over there asked that question. The throughput in phase 1 and phase 3 for VMs were not exactly identical to their shares. And the reason is because whatever I explained, the number of queue slots for a given host Though storage I/O control can manage that, but it will still be managed within the max queue depth that is set in the driver. Now, if I had increased the queue depth to something like 64 or 128 here, you would have seen the throughput exactly proportional to the disk shares of all the VMs and all hosts.
But you wouldn't have saturated the storage area.
Exactly. So in that case, what would have happened is because the latency of the IOs going to the data store would have crossed the congestion threshold I had set, storage I/O control would have been throttled down the queues further for the VMs that were running on host 1 and 2. And what would have happened is the workload would have said, that's it, I cannot do anything. The latency is too high, it would have crashed out.
I think part of the reason also is, I think what you're referring to is that the performance of VM 1 and 2 and 3 and 4 is not in ratio 1:1.5. And I think part of the reason also is that they are running, what Chetan is showing here is the application level metric. So there is another level of indirection where you get a certain number of queue slots that leads you to get certain number of IOPS, that leads you to get a certain number of DVD store orders per minute, and that is being shown here. And the fact that you got half the number of queue slots in one case may lead to less than half the amount of performance in DVD store. So the numbers won't match because of all these extra layers of complexities between them.
Just in general, OS overhead you have to overcome, and after that, it's all processing of the orders.
Exactly. And it also goes back to what Ajay was saying, that if the IO size is not the same, then the effect on application could be different, because one could be issuing very small IO blocks, and the other could be issuing a higher IO blocks. One could be issuing more reads, and the other one could be issuing more writes. So that's the effect. That's the reason why the throughput of the applications are not exactly in the ratio 1:2. If I had run IO meter, you would have probably seen it.
If we would have had more hosts and more VMs, so a larger sampling size, this would have probably, the reality of it, the throughput would start matching the shares.
Exactly.
True.
So that's a very, very keen observation. What would have happened in that case, as you have more hosts, the latency, exactly, the latency would start going higher more quickly, which means now storage I/O control has to reduce the total number of queue slots given to each host, which would have resulted in each host getting the sum of queue slots that each host would get would be something less than 32. And once that happens, then the throughput would have become more proportional to the disk shares. How did storage I/O control manage to do all this? I'll come back to the point I was just trying to explain, in fact, in this one. As you can see, in phase 1, the number of queue slots that were given to host 3, which was running the critical VM, was at its max, about 32. And it couldn't increase it beyond that because that was the max queue depth set in the HPA driver. The queue depth of the other hosts were approximately proportional to their disk shares. And when I say disk shares here, it's not the individual disk shares, but the sum of the disk shares of all the VMs that were running on the particular host. And you can see the disk shares of the host on the right hand, in the table on the right hand side. And this is something that you don't have to worry about, but I'm just showing here just for reference. In phase 2, as critical VM became inactive, you can see that the queue and total number of queue slots or queue length of that particular host dropped to the lowest value. The lowest value will be 4. And the queue depth of the other 2 hosts increased, and they were somewhere around 30 and 20. Once again, when critical VM became active, the queue depth in all the hosts returned back to their phase 1 level. You can also see that the overall latency on the shared data store was close to the congestion threshold I had set. In this case, that was about 20 milliseconds. The other thing you also want to pay attention here is, again, I'm showing the throughput of all the DVD store VMs, but if you look at the total throughput, the sum of the throughput of all the DVD store workloads that were running in all 5 VMs, at any given phase, they are pretty close. What this is saying is storage I/O control dynamically distributed the queue slots across the VMs based on their activity level, and because it was always helping these VMs get the queue slots they need, the overall throughput remained almost same, except the workload variation. The critical VM had highest load and the other VMs had lower load, but still it managed to redistribute the queue slots to the VMs that needed them. So the device utilization remained high throughout the experiment, which is something you need to remember. Storage IO control throttles the IO queue slots to the VMs based on their disk shares, but the main goal is also to keep the device utilization very high to protect the investment. What does this mean to you, VI admins? This is the third experiment that I'll be discussing, and the experimental test bed was similar to the test bed that I explained in test case 2. Without storage IO control, when I was running the critical VM by itself, performance was pretty good. Critical VM was happy. It was running at somewhere around 500 orders per second. This is the application throughput. When another VM became active, you can see that the performance dropped by 14%. 2 more workloads became active. Performance dropped by another 18%. When the last VM became active, performance dropped by another 10%. And at this stage, the total performance drop for the critical VM was about 42% from its peak value. And one workload became inactive, so the performance went up. 2 more VMs became inactive, performance went up further. And when only the critical VM was running, the performance was similar to the first phase. I know when Ajay asked if all the people who have storage problems could leave at the beginning, I didn't see anybody leave, so I'm assuming that you guys have some kind of storage problem. But how many of you have seen this kind of storage problem where one VM can hog the entire storage bandwidth and the critical VMs that are running on the same data store can suffer because of this one? Okay, there is some few people who have seen this problem. By the way, I know the problem is painful, but it was also very painful for me to create this experiment. See what happens when storage IO control was turned on. Same thing, critical VM was happy at the beginning. A VM became active, performance dropped by 14%. 2 more VMs became active, but performance dropped by only 8%. Last VM became active, nothing happened to the critical VM. The performance was still the same. But it was still 22% lower compared to its peak value. Now the VMs started becoming inactive. When the first VM became inactive, performance didn't change at all. 2 more VMs became inactive, performance went up. When the last VM became inactive, performance went back to its original value. Question by my co-presenter.
I have a quick question. So you're saying 22% here is definitely better than 42%, which is good. But I think some of us would lose sleep even on 22%. Is there any way to decrease this number further?
Is that true?
Will people lose sleep?
Okay, some people are nodding. So it must be true then. Yes, 22% is still high, but you should remember that I, the storage admin or the VI admin, had decided that I'm willing to tolerate certain loss in throughput, but I want to operate at a latency of 25 milliseconds. So at a latency of 25 milliseconds, obviously when all the VMs are sending IO requests, individual throughput of the VMs would suffer a little bit, because if you remember the latency IO curve that Ajay showed in one of the slides, as the throughput goes up, latency also increases. But as you start putting more and more load, the extra throughput you would get diminishes, but the latency starts increasing faster. Which means at 25 milliseconds, I would still see some drop in throughput, but I can do something about this one. And in the next slide, I'll show how to get more throughput. There was a question somewhere in the behind. No? Okay. I repeated the same experiment that I just discussed, but this time I adjusted the congestion threshold to different values. I wanted to see what happens. And I'll zoom into the congestion period, which is in the middle of the graph.
Just a quick comment. So the graph here is showing the performance of only VM5 for different congestion threshold values as you change it from 30 to 25 to 15.
The peak value of this critical VM is shown in the dotted line on the top of the graph that is at the bottom. So let's compare it to that peak value. What happens? Without storage IO control, obviously we've already seen that the throughput drops to about 42%. When storage IO control is turned on and the congestion threshold is set to 30 milliseconds, the drop was about 28%. When I reduced the congestion threshold to 25 milliseconds, the throughput drop was 22%. I reduced it further, and the throughput drop was now only 10%, which is good. It answers the question that Ajay asked. Now I can reduce the impact, or I can reduce the drop in performance of the critical VM. But there is a catch here. What you are telling storage IO control is, because I want to operate at a congestion threshold of, let's say, 15 milliseconds or less than that, storage IO control would now kick in much earlier and would start throttling the queue slots that are given to the VMs much earlier, which means the overall throughput of the device would go down. So the lesson here is, if you are concerned about the latency of your critical application, then yes, you would want to set the congestion threshold at a lower value. But if you are concerned about getting higher throughput from the device, then you would want to operate the congestion threshold at a higher value. Default value is good enough. Based on our experiments, we have seen the default value of 30 milliseconds can give you a higher throughput. But if latency is concerned, you can change the congestion threshold. At this stage, I would like to again welcome Ajay and give some tips for getting the most out of this feature.
Okay, so far we have talked about how the feature works, how to use it, and some of the real case studies. Now the question is, how do we best set some of the parameters that we have talked about, and we'll revisit some of the questions that were raised earlier about different data stores sharing the same RAID group. So the first best practice is basically, if it is the situation that your data stores are in fact sharing the same RAID group, try to use the same configuration parameters, which means that use the same congestion threshold at the very least. Because what would happen is, if two data stores are running on the same set of spindles, and if you set the congestion threshold to be 20 and 30, then one would start throttling at 20 milliseconds, and the other won't start throttling. It would keep on sending more IOs. Whereas the overall latency of these two data stores is already very correlated because of the underlying sharing. So we encourage that in any case where you are using it, first of all, one, enable the feature on all the data stores, because that means all of them would behave nicely. And the second, use the same congestion threshold in such case. Second is, since the feature is creating nice citizens, it is saying that if you see high latency, please throttle your workload. You want to protect these nice citizens from somebody who is not going to be behaving very nice. It's a very well-known TCP versus UDP issue, that TCP flows are being nice on the network, whereas the UDP flow can come in and hog everything. The same problem it would be if there is an external host or an older ESX host which is accessing the data store on which the feature is not even enabled, or it's a host which is not capable of running the feature, then that host won't throttle itself, but the others would. And we have actually gone a step further. Rather than just leaving the problem at this, we have built a detection mechanism in the feature where it looks at the stats and it looks at how the queue depth is being adjusted. And if the stats don't match with the expectation and the correlation between queue depth and the latency does not match, then it would actually send an alarm to the vSphere and say that the feature is detecting external activity on this data store. And in that case, we actually take some corrective actions in the feature as well, as in not to be too nice. We say we are detecting external activity, we don't want to be that nice anymore, and it would get into this mode where it would be a little more aggressive, and it would keep on detecting the external activity. When the activity goes away, it would be back into the nicest mode ever. And so in this case, you might get that alarm, and there is a KB article associated with that alarm. And if you see that, you can look at some of the possible causes for that in the KB article. And in case everything seems fine, but you still see the alarm once in a while, since we have built in a mechanism to detect the situation and handle it, I would say don't worry too much about it. You can even ignore the alarm in some of the cases when it's happening very occasionally and you are running sort of a supported configuration for the feature.
That seems to have serious implications for the snapshot-based backup programs, like the backup and recovery, or I can't think of any others. They snapshot it and they're going to pound that data store, or not the data store, the RAID group.
True.
Or check for change blocks. So that's going to
Exactly. So I think if that is so, in the KB article, if you read, we have listed cases like this, and we are basically saying if you are aware of these issues and that is what is causing the alarm, you can just ignore the alarm for that time, because that backup is causing high latencies and the algorithm is just detecting it for you. It is saying, I am seeing some external activity and I am telling it to you, and you can just ignore the alarm. But it can also happen if, let's say, you are not aware of any such activity and there are older hosts accessing their data store without you knowing, then the alarm would tell you that you should do something about it, and that would give you at least a heads up.
So if I search for SIOC and external activity online,
You'll find the KB article, yes. Sure.
You said it doesn't involve vCenter, but now you mentioned not to share across vCenter servers.
That is basically, you should not share the data store across vCenter servers. Again, the issue is, high-level issue is the same, that if you have one data store which is accessed through host in two different vCenter servers, you enable the feature in one and you don't enable the feature in another, it's going to detect that vCenter host as external activity. So if you do share, you can, it's unsupported configuration to share it, but if you do share, what you can do is you can enable the feature on both sides with the same congestion threshold, and it would be fine. And the last thing is about the congestion threshold value. As we mentioned earlier, that this is the single most, this is the only parameter setting that goes with the feature. And we have put by default the value of 30 millisecond, which in my opinion is sort of a conservative value, because by the time you are hitting 30 millisecond, you cannot get any more IOPS out of the device typically, but the feature would not allow the latency to go any higher than 30. But if you are running your data store on, let's say, SSDs, then you want to definitely bring that value down to maybe 10 or 15. If you are running on fiber channel, I think 20 to 30 is a good range. I have seen in my own experimentation that when we set the latency threshold to be 20 millisecond versus 30, if you run the IO meter workload on the data store, you can squeeze in another 20% of throughput by going from 20 to 30. But now the question is, do you care about that extra throughput that you might squeeze in by running something like IO meter, or do you care about operating the data store at 20 millisecond? There is also a question about auto-tiered storage arrays. In that case, if you are actively moving your own LUN from one kind of tier to another tier, then you can change the latency threshold as suggested above. And in cases where the LUN is actually spread across tiers, in that case, either you can pick a value in between, because what would happen is the faster tier would bring the latency down and the slower tier would make the latency go higher. So you can pick a value in between, or we have asked vendors to recommend a setting based on the configuration of a LUN on different tiers in the array. And now to conclude, we believe that SIOC is a great feature in providing the performance isolation to different VMs and making sure that one VM cannot really pound on the data store, hurting everybody else's performance. And we have shown that SIOC is very smart in terms of detecting the congestion and also acting on it dynamically. If there is a VM that goes idle, the VM doesn't have to be powered off or something. If the workload stops, it would automatically allow others to send more workload, and it would keep on adjusting to the workload. And it would be hope that everybody would use it. Any kind of feedback and review is highly appreciated, and we hope that it would protect your critical applications during the I/O congestion period. And if you're seeing high latency throughout the day, maybe you should just go and buy more storage, because this is not going to be helping you too much. But if you have storage and you're seeing high congestion, higher latencies, half an hour during the day, 1 hour during the day, then the feature would really protect you during those times when you are seeing it. So it could be that you are seeing it once in a while, 10 minutes now, 20 minutes later, and so on. And that's where feature would really protect you, because for that half an hour, you don't want to go and put in more storage into the data center. And yes, that's actually a very good question. I'm glad you asked. So right now, there is no explicit report that you can get how often it kicked in. But if you go to the data store performance page, it shows you the queue depth of the host, and you can see in a typical scenario when there is no congestion, it would be a flat line sitting at 64 or 128 or 32. If you see that that line is moving, that basically means the feature is kicking in, because nobody else is going to be changing the queue depth at the host. But that's a very good feedback. We are actually looking into providing sort of a statistics on for how long it was kicked in and active, and for how long the congestion lasted. But for 4.1, we don't have that feature. But that's a good comment. We also have published a lot of work in terms of understanding the feature, making sure that you get the best out of the feature. We have some of the white papers in terms of how to use it for your applications. We also have a conference publication that actually talks about real nitty-gritties about the algorithm, what control equation we are using, and a lot of other things. So I would encourage people to actually go and read some of the publications to really understand what's going on if they are interested. And finally, I think you should use the feature, and it would allow you to consolidate more, over provision less, and sleep better.
Feedback.
And